Hello friends. Welcome to Electrical Machine Class Lesson 7. In this lesson we will learn about speed control of DC motors. We will discuss flux control, armature resistance control and voltage control methods. Why are DC motors still in use yet the available electric current is alternating current? DC motors are still in use because they have a fine speed control, that is, its speed can be changed over a wide range by a variety of methods. The speed equation of a DC motor is given by N equals V minus E Ra, K dot operator phi. Where 1. N equals speed in RPM. 2. V equals applied voltage. 3. I equals armature current. 4. R equals armature resistance. 5. Phi equals flux per pole. 6. K equals constant depending on motor design. Thus motor speed can be changed by varying voltage, V. Armature resistance, Ra. Flux, via field current. The methods used for speed control are voltage control, achieved by varying the applied voltage. Armature control, achieved by varying the armature resistance. Flux control, achieved by varying the flux per pole. In video number 5 on characteristics of DC motors, we learnt that the speed of DC shunt motor is inversely proportional to flux. By decreasing flux, speed can be increased and vice versa. The flux can be changed by changing shunt field current by using a field rheostat. A field rheostat is added in series with the shunt field winding. The rheostat reduces shunt field current and hence the flux. Note: this method is applicable to both DC shunt and compound motors. The below is a circuit diagram of flux control method. The field rheostat is connected in series with the shunt field winding. Let us now look at the advantages and disadvantages of flux control. Advantages: 1. It's an easy and convenient method. 2. It's efficient. 3. It's inexpensive. 4. Its speed control is independent of the load. Disadvantages: 1. Only speeds higher than normal can be obtained. 2. There is a limit to the maximum speed obtained by it. Let us now look at armature control method. This method is based on the fact that by varying voltage across the armature, the back EMF and thus the speed of the motor can be changed. A variable resistor is inserted in series with the armature. Due to the drop in voltage in the variable resistor, the back EMF is decreased. Since speed is directly proportional to the back EMF, the motor speed is reduced. The highest speed obtained correspond to the variable resistor being equal to 0. Note: is commonly used in series motors due to the disadvantage of poor speed regulation, which isn't important in series motors. Advantages: 1. Constant field current and torque. Disadvantages: 1. A large amount of power is wasted. 2. The output and efficiency of the motor are reduced. 3. It results in poor speed regulation. 4. The speed varies widely with the load. Let us now look at the circuit diagram of armature control. As is shown, the field rheostat is in series with the armature. Let us now look at voltage control method. In this method, the supply voltage source for the field is different from that of the armature. There are two types. 1. Multiple voltage control. 2. Ward-Leonard system. Multiple voltage control. The shunt field of the motor is connected permanently across a fixed voltage source. The armature is connected across a variable voltage source. The speed will be proportional to the armature voltage. A shunt field regulator can be used to obtain intermediate speeds. Ward-Leonard system. In this method, the shunt motor whose speed is to be controlled is connected directly to a DC generator driven by a constant speed AC motor. The field of the shunt motor and the generator is supplied from a constant voltage exciter. The voltage of the generator is varied by means of its field regulator. A field regulator can be included in the field circuit of the shunt motor for additional speed adjustments. Advantages of Ward-Leonard: 1. High efficiency, as the speed of the motor can be adjusted through a wide range without resistance loss. 2. The motor can be brought to a standstill quickly by rapidly reducing the generator voltage. 3. Used for speed control of large motors when DC supply is not available. Disadvantages: 1. A special motor generator set is required for each motor. 2. The losses are high in this set if the motor is operating under light loads for a longer period. The circuit diagram below is of Ward-Leonard control. The single-phase AC motor labeled M1 is the prime mover of generator, G, whereas motor M2 is the one whose speed is to be controlled. Now let's look at the speed control of series motors. Uses the below methods. 1. Flux control. 2. Armature resistance control. 3. Series parallel control. Flux control. In this method, flux is varied and thus the speed varies too. This is achieved by using field diverters, armature diverters, tapped field control or paralleling field coils. Field diverter. A variable resistance is connected in parallel with the series field winding. This resistance shunts some portion of the line current from the series field, thus weakening the field and hence increases speed. The below circuit diagram is of a field diverter. As is shown, the diverter is connected in parallel with the series field. Armature diverter. In this, a variable resistance, armature diverter, is connected in parallel with the armature. The diverter shunts some of the line current, thus reducing armature current. The reduction in armature current results in increased flux and thus reduces motor speed. Note: torque is directly proportional to the product of flux and armature current, and speed is inversely proportional to flux. By adjusting armature, diverter speeds lower than rated can be obtained. It is applicable for constant torque loads. The circuit diagram below is of armature diverter. As is shown, the variable resistor, armature diverter, is connected in parallel with the armature. Now let us look at tapped field control. In this, the number of turns of series field winding are reduced, resulting in flux reduction and hence increased speed. The field winding of the motor has a number of tap points along its length. You select the number of turns of the winding to be active by connecting the power supply to different taps. Connecting to a tap that has a larger number of turns results in more field current, stronger magnetic flux and thus lower speed. Connecting to a tap that has fewer turns results in less field current, weaker flux and high speed. The circuit diagram below is of tapped field control. As is shown, the series field can be tapped at any length. Now let us look at paralleling field coils. In this, the way in which field coils are connected, that is series or parallel, is changed. This alters the total resistance of the field winding. A lower resistance in the field winding results in more current flowing, flux is increased and consequently speed decreases. Higher resistance in the field winding results in less current flowing, reduced flux and thus increased speeds. It is used to provide multiple discrete speed settings for fan motors. The circuit diagram below is of paralleling field coils, usually employed in the case of fan motors. Now let us look at armature resistance control. In this method, a variable resistance is directly connected in series with the supply. This reduces the voltage available across the armature and hence the speed falls. By changing the value of variable resistance, any speed below the normal speed can be obtained. Is commonly employed to control the speed of DC series motors. It has poor speed regulation. This has no significance for series motors because they are used in varying speed applications. The circuit diagram below is of armature resistance control. As is shown, the field rheostat is in series with the supply voltage. Now let us look at series parallel control. In this, two or more similar DC series motors are mechanically coupled to the same load. The two or more motors can either be connected in series or parallel. When the motors are connected in series, each armature of the motor will receive half the supply voltage, thus speed will be low. When the motors are connected in parallel, each armature of the motor receives the supply voltage, thus speed will be high. Note: for the same load on the pair of motors, the system would run approximately 4 times the speed when the machines are in parallel as when they are in series. The circuit diagram below is for series parallel method. As shown, when the connection is series, the voltage in the armature is half the voltage of the supply. When the connection is parallel, the voltage in the armature is the same as voltage of the supply. Now let us look at series parallel and resistance control. In this, series parallel is combined with resistance control. At standstill, the motors are connected in series via a starting rheostat. The motors are started up in series with each other and starting resistance is cut out step by step to increase the speed. When all the resistance is cut out, the voltage applied to each motor is about 1/2 of the line voltage, and thus the speed is also half what it would have been if full line voltage had been applied. To increase the speed further, the two motors are connected in parallel and at the same time the starting resistance is connected in series with the combination. The starting resistance is again cut out step by step until full speed is attained. In summary, shunt motors. Method commonly used is flux control, that is for above normal speed, and armature control for below normal speed. Series motors. Method commonly used are field diverter and armature diverter methods. Voltage control are used when smooth and wide range control is needed. Thank you for watching our channel. Like, comment, share and please don't forget to subscribe. May God bless you.